third session. So today we are entering the core of this mini course. And so let me summarize what we have learned so far. So what we have learned so far is that so we had on one side this equation. From which, basically, we were able to define in a suitable limits a measure. This is what we would like to call the turbulent measure. That was basically what we wanted to do. And on the other side, what we did last time, we said, okay, we may as well try to describe this measure. That's the first box here. And we may as well try to describe this measure, and we may as well try to say that this measure is low something Gaussian. That's what we call the Gaussian hits. And the connection between those two objects was done in terms of symmetries. Statistical. And apart from homogeneity, isotropy, and stationarity, the important symmetry that is at stake is the scaling symmetry, something which we want to claim is that an equality in law between delta u x and t and lambda h delta u x over lambda t over lambda 1 minus h. And what we saw is that if you model basically the turbulent measure by a very non-offensive Gaussian, then you wind up with a process which looks like that, and that you realize this symmetry with, say, h equal 1/3, for example. So you restore this symmetry. But on the other hand, what we saw at the end is that, okay, if we look at the real Navier-Stokes signals, it doesn't look like that. It looks like that. And, you all passed the test. Well, collectively, we passed the test last time, that we were able to distinguish between Gaussian and Navier-Stokes. So it means there is something different here. It means that there is something different. And the difference between Gaussian and Navier-Stokes is what we may call as anomalies. The physicists call that anomaly. In fact, it's totally normal. But okay, let's call it anomalies just to go with the current jargon. And of course, if we think about turbulence, there are at least, there are two important anomalies which make this different from this. The first anomaly is one that we talked about during the first course. It's basically a dissipative anomaly. Saying that, in fact, you need to be non-Gaussian to dissipate, okay, for reasons that I think we won't have time to explain, but that's one example of anomaly. And the other anomaly which is important and which is the focus on today's lecture is basically a scaling anomaly, so an anomaly at this level. And essentially, this scaling anomaly is the topic of today's course. And this scaling anomaly is something that we usually refer to as intermittency. Okay, and so that's course 3. And so to begin with, let's try to see what exactly we mean by scaling anomaly. And so to see what we mean, let's just go back to the Gaussian case. Where basically we had seen that this equality holds at the level of increments. So remember, so for example, if we had, so we were describing a parallel correlation as a correlation with a power law scaling with 2/3 here. So that if you want to extract this component, you just look at delta U parallel is equal to U parallel of R minus U parallel of 0. And this basically is behaved as a Gaussian, which has a norm, which has a 0 mean, and which has a variant which is twice this number here. So that's if you plot delta U square, for example, this has up L, and you have a 2/3 R over L 2/3 here times 2U0 square. Okay. And so this means that basically, if I put this guy away, okay, so I can say that, so this is the variance. So this is also the same thing as just taking a Gaussian, which is 2, I think the square root of this guy, R over L 1/3 times the unit Gaussian. Okay, so in terms of representation, what it means is that, of course, if I plot, so if I plot, say, the PDF of delta U parallel, that will be the PDF distribution. As of, for different L, so when I will have a Gaussian when I take L equal say L, and if I take a different L smaller, then I will have something more peaked like that. So that's if I don't rescale. For I take L smaller than L, that's L, for example. But this property tells me that if I divide by the good quantity, so essentially by this quantity, so I put delta U parallel divided by, so here, the 1/2 of the variance. Then I will recover a Gaussian for this one, and the other one, this one, will just superpose perfectly. Yeah. So that's really scaling variance. as one can envision it. Now, so that's the Gaussian case. Now for Navier-Stokes, it's a bit different. That if you do the same trick, so for Navier-Stokes, if you do the same, so that's for Gaussian. Okay, so that's Gaussian here. And for Navier-Stokes, so you may, okay, if you look at delta U parallel as a function of the scale, it will be apparently the same, something which is more and more peaked as you go towards the small scales. But if you rescale it, PDF, so that will be delta U parallel square 1/2. So the one at L will probably rescale nicely towards the Gaussian if you force in a good manner. But the one here will not rescale. And in particular, there will be some fat tails. Some slower decay for the PDF of delta U, even though you have normalized by the variance. So this is an example. So basically, this is an example of a case where if you rescale, you don't get the same statistics. So it's typically what we mean by a breaking of the scale invariance. So breaking of scale invariance. And so, for example, if we were to look at a signal, what would it mean? Is that I will plot a signal of say delta U of x minus of L plus L, x plus L minus U of x, well, something like that. If I plot the difference, I will see something very Gaussian. So it will be at L equal L. And then if I try to do the same thing, but at scale, which will be smaller, say L equal eta, where eta is a Kolmogorov scale, and I plot U of x plus eta minus U of x as a function of x here. This is what I will observe. Something very peaked. So obviously, even on this drawing, you could not mistake this guy for this guy. You could not say they are the same. It would, you would not need a collective effort to say they are different. That's so that's basically what's happening when we said that there is a breaking of scale invariance. The PDF are not the same depending on the scales at which you are looking at. And so the question is, how do you quantify this effect? How do you quantify this effect? And so one possibility, and so one solvable which is used is basically to use structure functions. Okay, so what we have been focusing on are basically increments of my signal. So if I take an increment, say delta U parallel to be simple, which is U of x plus L minus U, let's suppose it's homogeneous, okay? Then the way to, the traditional way of defining a structural function is to take absolute value of this guy, a power, P, and an average. And this I will call S P of L is the pth order structure function. So intuitively, what does it mean? So for example, take P equal 4, just to have an idea. So P equal 4. So S4 of L will be the integral of delta U 4 times the probability of delta U parallel D of delta U parallel. That's what we are doing. And so basically, with that, we are integrating against the variable a compensated PDF. And so if the PDF, if that was, if that's P, if I multiply this by delta U4, what I'm doing is that I'm putting this to 0. And so close to 0, I will be Kartik. And then I will put some weight in the middle. So it will be something like that. Okay, so that's delta U4 times P. Okay, so basically, if I put a positive power here, I'm just probing the tails of this guy. So the higher the power, the further away I can probe the tails. And so in what is seen, and that's an observation. Observation, which was one of the numerical observations that we did to define the Gaussian measure, is that basically in Navier-Stokes, the structure functions display power laws. So typically, something which will be that SP of L will be proportional to L over L to the power certain function, zeta P, times the structure function evaluated at the larger scale here, when L goes to 0. So when I say L goes to 0, of course, it's the case where I'm taking the turbulence limit, where nu is already goes to 0. So in practice, as in the case of the second order structure function that we discussed the other day, this is true essentially in practice between some small scale eta and for some large scale L. That's what I mean by L goes to 0. And so we see that basically we have those, there are some zeta p's here. And so the zeta p's, zeta, and so the zeta p's are the scaling exponents. So what should we expect for those scaling exponents? So let's take again the Gaussian case so that we know what we should expect. So scaling exponent Gaussian heat scaling exponent. So for the Gaussian heat, we have that delta U parallel of L is, as we saw, that the same in law as 2 U0 L over L 1/3 times delta U parallel of L, which is the normal with 2 U0 square as a variance. And so if you take the power P here, average, this equality it becomes an equal sign. This is just a prefactor, and so we just need to put this to the power P. Okay? So now we can just extract, so what is important is basically this prefactor here. This 2U0 is not here. So this basically will be only L over L to the power P over 3. And so that's basically the scaling exponent zeta P Gaussian is P over 3. That's something that usually we refer to as the K41 scaling. Or the scale invariant scaling. So scale invariance here provides a linear behavior for P. And so in particular we can look, so one way that we can explore the consequence of this scaling behavior is basically if we so we want to try to quantify how picky I am. Okay, so one way to characterize deviations from Gaussianity is to compute something which is called the flatness. So, for example, if I define the flatness, I'll call f of L will be delta U for L divided by delta U square L. It will be S for L divided by S2 square L. And that will scale exactly as L to the power zeta P, zeta 4 minus 2 zeta 2. Okay? Up to a constant, which in the case of a Gaussian homogeneous isotropic turbulence is 3. So zeta 4 is here 4 over 3. 2 times zeta 2 is 2 over 3 times 2. So that's here 0. So that's exactly 3 for Gaussian. And so now comes the observation. So Navier-Stokes observation. So let's plot the flatness as a function of the scale. So let's put it as a function of L over L, L being the largest scale. And so if you are at 1 is the largest scale. And let's not put F, let's divide by 3. So that basically the reference will be 1 here. So for a Gaussian, that's that. Okay? And now let's measure it for Navier-Stokes. Large scale, you force it well, it's approximately here. Then let's divide by 2. At 2, you begin to see the small deviations here. Not large, something like it's not 1, it's 1.07. 1/4. Another deviation here, which is not large, 1.13. 1/8. Another deviation, not large, 1.21. Etc., etc. And so the question is, what's happening here? So we have two options. So if you see that, well, we are just going to 0. 0 is here. That's why it's not large. So we may as well, maybe we are going to converge here. We don't know. So basically, in order to probe this region, usually what we do is that we plot the same thing in log scale. And so let's do a zoom here. A zoom. And if you do a zoom in log, so let's put log 2 of L over L and log 2 of F over 3. Then at 0, you are the log is 0. And then basically, this is what you see. You see a straight line. And the slope here is exactly minus 0.1. So all the numerics and all the experiments of turbulence, they produce this type of pattern, where basically we are forced to conclude that F of L is something which will be 3 times L over L power minus 0.1. So this means that so it's always hard to interpret a log plot, but if you go there, this means that this is not what's happening here. What's happening is this behavior here. So you have a divergence of the flatness. So here, essentially, this goes to infinity when L goes to 0. So if you want to describe a turbulent field, then you clearly cannot use a Gaussian field. If a Gaussian field has finite value, stupid finite value f equals 3 for the flatness, while a turbulent field has infinite flatness. So in terms of, if you want, what I was not exaggerating enough when I was plotting the PDF of So for Navier-Stokes, when you plot delta U parallel as a function of, or PDF, sorry, as a function of delta U parallel divided by delta U square. So indeed, when you go, that's for L, in fact, that's for L, and then basically when L decreases, the signal becomes more and more peaky until basically when L goes to 0, it becomes infinitely peaky. So it, super sharp. Flatness is infinite. So the question is okay, there are two questions. What do we do? How can we describe such a field? First question for probabilists. And then the other question is how can such a dramatic PDF emerge from the Navier-Stokes equation? We need to come with something better than a Gaussian here. And we need to come with something better than this idea of just statistical restoring of symmetries with h equal 1/3. And so here, basically, this is I want to propose a scenario on how this could happen. And usually, to propose a scenario, we use toy models. So here, I will use a small toy model, which I will call the random H model. So let's a bit idealize Navier-Stokes.
Before you erase, let me ask a question. So there are a lot of probability distributions, not only Gaussian fields.
Yeah.
I would be very surprised if probability didn't prevent processes, yes, it would be non-Gaussian processes, yes, which would satisfy such a statement.
Yeah, so such probabilities exist. Like the closest thing we have to turbulence is something which is called Gaussian chaos, probably. And it's not the topic of today, but if you want more, you can ask André. He knows everything about it.
But would we be able to distinguish pictures of Navier-Stokes and the Gaussian chaos?
If you want, we can make a test during the coffee break. But yes, the answer is yes, because in fact there are many properties, and in particular, if you want to, of course, you can refine. If you want, basically, maybe the closest that we have to a turbulence signal is a 1D signal that was proposed by Chevillard, Garban, and Rod in 2018, which is a process which has this property and which has some skewness, which is very much like what we see in Navier-Stokes, and which is built using Gaussian chaos, essentially. So that's, but it's not perfect.
So there is no distribution known in probability which you cannot distinguish from.
As far as I know, I can show you some picture, and you see that still, I mean, you can see that you can tell that they are not the same. So really, we are close, but we have a pretty good idea of the spatial structure. But on the details, there are still there is still some room for improvements. So here, basically, and of course, those models are just models that are like magician models, like a model that you just take out of the cup of a cup of tea. Like, say, oh, okay, looks like, and that's totally data-driven. So here we want to have something which is, okay, we want to have a connection which is more anchored in the dynamics. And so how can the dynamics create something which is skewed, or which is, flat in the sense of flatness? So let's propose a probabilistic vision. And the probabilistic vision will be the following. So I will take a discrete model. And so assume that I have some type of particles which are a turbulence structure, okay, which will be described initially by a size 1. And okay, it moves as a function of time in my domain. And then after a time t0, it splits into 2. So I will have L1 equal 1/2. Okay. And after a time t1, it splits again into 2. So I will have a scale L2 is 1/4, etc. So that after I repeat this process a certain number of times, the typical size of that structure will be Ln, say 2 to the power minus n. So I need to attach a variable to this guy. So let's think of, let's call it U0. Okay? And the way we should picture this thing is essentially it represents an increment of a field at scale L0 times tau 0. Okay? So basically, UN will be delta U parallel Ln tau n. And so now I need to specify what I mean by what are the dynamics of those tau n's. And I have an h here, so I need to introduce an h. So let's assume that at each basically step of this process, I have an h, h0, h1, h2, hn. And I will relate the time of life of the structure at time tau 1 to the time of life of the structure of the preceding time. So I put by hand basically this rule. So this is where there is still a rabbit here. Okay, which is, I just say that tau n will be tau n minus 1 times 2, 1 over 2, 1 minus h n minus 1. Okay? Let's put it this way. Tau n plus 1 is tau n 1 over 2, 1 minus h n. So if I do that, then basically I put this rule, and the second rule is that u n plus 1 will be 2 to the power minus hn un. Okay, so with this rule, basically, this rule plus this rule plus this rule, they realize in a random manner a statistical conservation, a scale invariance at each step, which is prescribed by the hns. In the following sense, is that u n plus 1 equal to this thing, delta u parallel of L n plus 1 to n plus 1. So that's delta u parallel ln over 2 to n over 2, 1 minus hn. And so if I impose my delta U parallel to be scale invariant, then I will have exactly 2 minus Hn delta U parallel of Ln tau 1, which is 2 minus Hn Un. So basically, this simple model with these simple rules, it realizes the scale, and I put a low here. It realizes a scale invariance of the Navier-Stokes or whatever dynamics you want that has a property that you can relate the structure at a given scale to the structure at a larger scale, except that it's compensated with this Hn, which fluctuates from scale to scale. So that's it's a 2 minus, yeah. It should be, yes, there it was not erased. 2 minus, yes. So if you decrease the size of the observation, you decrease the size of the structure, and you decrease the time with which you win. So that's the model. So basically here, let's explore the consequence of this representation for the structure functions, or for basically the production of a scaling exponent. Let's just write. And so let's take a simple scenario. Assume that the Hns are drawn according to a distribution H and independent. In the sense that they are independent and identically distributed. And the HIs are just toss a coin each time. And so let's try to write down. So that under this hypothesis, let's just try to write the Un to the power P. Okay. So Un to the power P will be 2 minus P times Hn minus 1 U n minus 1. It will be 2 minus P times the sum from I equals 0 to n minus 1 of Hi. Let's not do it this way. Un minus 1 to the power P. It will be 2 minus P H minus 1, 2 minus P H minus 2, 2 minus P H0 times U0 to the power P. So if I take an average here, I have an average here, I have an average here, and because the HIs are all independent, this is nothing but 2 minus P H average to the power n times U0 P. So this is this one here. So basically, when I do that, so that I take the average, and because the small h's are independent, I just and so I have n time the same object, and that's what I call 2 to the power minus ph. Okay. And so here, basically, if I continue, then UNP is exactly 2 to the power minus n zeta p times U0p. Well, this is nothing but ln to the power zeta p. We call that ln is 2 to the power minus 1. With zeta p, which is exactly prescribed by taking a convenient log on this expression over there, which will be the log of 2 minus the log 2 of 2 to the power minus ph. Okay? And now let's play games again. Let's take some various h's. So let's take some examples. First example, I will take, say, h, which will be just, say, a delta function. That p of h is represented by just h, h0 here. Oof. Okay. So basically, it's a deterministic case, stupid. And in that case, then 2 minus ph is 2 minus p h0. So zeta p is minus, it will be p h0. It's linear with p. So it's the same as, so typically take zeta p, the function of p, poof, p h0. So h0 equal, again, 1/3. We covers K41 scaling. Okay. Now, and that's what we call in the jargon. There is one h, so we call this monoscaling. Okay. So now from one h, let's put 2h. And do you want t at this point? So let's grab some t and then put another h. So back in 2h in 4 or 3 p.m. 5 minutes. It's 4:08 sharp. Exactly the time that we announced. So let's continue this game. So let's put 2 guys. Say let's do it simple. say let's take mu 0 times delta h plus, I don't know, 1 minus mu 0 times delta 1 minus h. It's simple. Where mu 0 is between 0 and 1. So that basically I want to have a distribution of h where I have that's 0, that's 1. I have some mu 0 here. And I have some 1 minus mu 0. Okay? I have some probability to have here and here. And so if we do the computation, then we compute this guy. So 2 minus ph will be mu 0 times 1 plus 1 minus mu 0 times 2 to the power minus p. 1. Okay. So the scaling exponent will be minus log of 2 of mu 0 plus 1 minus mu 0 times 2 to the power minus p. Okay, so what does this look like? So just keep this expression here. Minus. So what does this look like? So when, say, when P is very large, then zeta P is the same as log 2 of mu 0. So if we draw it, we have P, zeta P, so P very large is here, which is log 2 of mu 0. And say when P say go to minus infinity, for example, very large but negative, then zeta P, so only this one will contribute. So it will be zeta P will be minus log 2 of 1 minus mu 0 2 to the power minus p. Okay, it's minus log 2 of 1 minus mu 0 plus p log plus p. And so when I'm very negative, I will be just p like that. Okay. And when p equal to 0, I can compute that zeta 0 is mu 0 plus 1 minus mu 0, so it's 1, so it's 0. So we have something like that. So what is the behavior that we can expect? Maybe something like that. So maybe here, up, and then we need to match to this asymptotics. So something like that. So you see, it's very easy to create zeta p, which is not linear. It suffices to put like a competition between two scaling. And here, basically, what we see is that this one here, which we call H mean here, contributes to here. And this one here, which we as well call H max, contributes to this scaling. Now the slope, it determines the slopes at both ends for the scaling exponents. And so this example, where we have just two slopes here and something just something in between, is something that is called biscaling. Okay? And so from monoscaling to biscaling, then the next step is multiscaling. And multiscaling will be something which will be achieved by taking our favorite, this will be the third example. Maybe just take a continuous distribution of H. Assume I take H, which will be C1 sigma 2, normal with mean C1 and variance sigma 2. Then, this I will erase. So, to compute this, how do we do? So that's 2 to the power minus P H minus C1 times 2 to the power P C1 minus, okay, then I take an average, okay, and also this is the exponential of minus P log 2 H minus C1. And this type of quantity, we can know them by heart. So this is, those they know them by heart. It's a P square over 2 log 2 square H minus C1 square. So it is a characteristic function of something which is Gaussian. So the variance is appearing. And so there is a log 2 here which appears. So this is 2 to the power P2 over 2 log 2. And H minus C1 square is exactly sigma 2 square. And so 2 to the power minus pH will be 2 to the power P2 over 2 log 2 sigma square minus P of C1. And so take the log of this guy, the log 2 of this guy, and you will wind up with the zeta p's. So zeta p's equals, so it will be PC1 minus P2 over 2 log 2 of sigma 2. And so let me call that C1, C2 as a shorthand. And so basically, this describes a case where you will have a pure scaling which will be modified by a parabola. Something like, so you are going to start here, up, and oh, then you have a parabola. Okay. And so some applications, some numbers, perhaps, but this I don't. So it turns out that for Navier-Stokes, this type of formula provides a very good approximation with C1 equal to 0.37 and C2 is equal to 0.25. Okay, which essentially prescribes, so this in particular prescribes that zeta 4 minus 2 zeta 2 equal minus 0.1, for example. And so what does it describe? It describes basically here a PDF of H where your Gaussian centered on C1 and with here it will be sigma 2. And here C1 is approximately 0.37, and so you can observe that this value is greater than 1/3. For example, which will be the K41 scaling. And so, as a matter of, so just some numbers. Typically, for P, with this scaling, when 1, 2, 3, 4, 5, zeta P will be 0.35, 0.69, 1, 1.29, and 1.59. So those are numbers which are kind of, except for this guy, which is 1 here, that comes from, okay, I won't discuss today. Those numbers are nothing. They look like random numbers. Nothing close to 1/3. So this 1/3 that we imagine for the K41 scaling seems totally out of reality for turbulence. And so basically, this type of models tells you that turbulence. So we have seen that the turbulence was a machine that dissipates energy. Okay, the first lecture. That turbulence is basically a machine which entangles the scaling symmetry. Meaning that in a sense, if this type of picture is true, then the fact that we don't recover power law is not just an artifact of breaking the scaling invariance. It's just basically that all the H are allowed and they are recovered at the same time. They're just totally entangled. And so, of course, one of the questions that you may ask is how do we, in practice, how do we compute P of H from the Navier-Stokes? So that's a question. Basically, how you determine it quantitatively and what's the mechanism. So just just a small refinement on this argument. So this model is here. We have made a very convenient hypothesis, which is the fact that all the H's here are independent. So in fact, we can simply try to work without this hypothesis, and that will be, in fact, quite informative and perhaps closer to the truth. So let's just make this argument. And so let's call this the multifractal theory. Multifractal theory. Like a toy model of a multifractal theory. So let's just, so here we had, now let us not assume any longer that the HNs are IID. Okay, but we'll make somehow a weaker hypothesis. So let's define Hn, capital H, which will be 1 over n for the sum from I equals 0 to n minus 1 of Hi. So this is something which we may call sample mean. Okay. And so and then basically we're going to assume that there exists a so-called large deviation principle. In that the probability that Hn takes some value in the H has to be given asymptotically by something that we will call n to the power d of h, for n goes to infinity. So that's the case, for example, if you suppose that the HIs are RID, and they are Gaussian, for example, because the sum of Gaussians, you will recover a Gaussian with n times the variance. So d of h will be nothing but basically what's appearing in the argument of the Gaussian when you suppose that the h or I is in Gaussian. But here, let's work a bit more generally. And so in that case, let's to compute again Un of p. So in that case, Un of p, Un to the power of p, it was 2 to the power minus Hn minus 1, 2 to the power minus H0, U0p, and there was a p here, okay? With some average here. And so here, basically, this is nothing but 2 minus p times sum for I equals 0 to n minus 1 of hi times U0p. And here we recover exactly H. That's exactly n times Hn. So this is U0p, the same, times 2 minus p of n Hn. Okay, so now we can compute it thanks to this property. So this is U0p times essentially 2 minus p, put an integral, 2 minus p of nh times the probability that I have in nh times the probability that hn is in dh. So sorry, I forgot an dh here. Okay, and that's exactly. So essentially, we obtain that UNP is U0p times the integral over dh of 2 to the power minus p and h plus n dh plus n dh. Okay? So this is 2 to the power minus n ph minus dh. Okay? And that's equivalent when n goes to infinity to essentially u0p times 2 to the power minus zeta p, where zeta p is nothing but the infimum over h of ph minus dh. So basically, here, zeta p appears as a Legendre transform. Fenchel transform of the A of h. And if so if psi of p is smooth and differentiable for p is in R, then we can invert this relation, and then we obtain that. And so we obtain if psi of p is smooth and concave on R, then d of h is basically the infimum over p of ph minus zeta p. And so you have basically a mediation between, on the one hand, zeta p, and on the other hand, d of h. And so typically, for the case that we saw, if zeta p typically has this type of behavior, imagine that zeta p has say an asymptote here, which will be p h min, and here another asymptote here, p h max. Okay, as a function of p, then d of h will be something that will be that will look like that. Typically, d of h like that. Will be between h min and h max, completely supported with bell-shaped. And so, so for more on that, I can only recommend a review by Touchette, which is 2010, I think, on Legendre Fenchel transforms, which tells you how, under which condition you can invert basically those type of relation. And basically, in the language of, there are two things. So in the language of turbulence, this quantity d of h, which is nothing but a rate function, is called, it has a barbaric name, d of h is basically called the singularity spectrum. And so what does it represent? So what does basically P of, so interpretation. So P of Hn in the H is basically the probability that Un has a pure scaling law mediated by a given H. Okay. And so this is basically the probability that P of delta U is exactly L to the power H. So call that SH. Okay? And so basically, if you can imagine that in a real life turbulent flow or in a real life setting, SH will have a weird shape. And in fact, it will be some type of fractal. And so if you launch a small ball here in the domain, then the probability that the ball epsilon will intersect SH will be something like epsilon to power d minus dh, with d being the dimensionality of the domain. And here, in our case, because there is no dimensionality, we just took d equals 0 in our d equals 0. So d equals 0 for the random H model. And so that's why, basically, this multi-scaling view, which is prescribed by the random H model, is sometimes called the multifractal framework because of this interpretation. So in the language that we will use, multi-scaling will be used, I think, in a somewhat interchangeable way with the word multifractal. And so to conclude, some openings. So here we have seen that essentially the intermittency is a very strong part, like an essential part of turbulence. That we need to describe it, and we need to know how it arises from the equations. And so openings, basically, there could be many ways. So basically, some readings. So for multi-scaling, basically for intermittent field. So if we want to extend the Gaussian picture to intermittency, then basically this is basically the realm that we were discussing previously of say Gaussian chaos. And so we can read basically Chevillard, Roth-Vargas, (2018), for example. And then if you want to interpret dynamical interpretation of, say, multiscaling, then you have a theory which was known, like which has prevailed like since 2000, basically from the years 1990, 2000. Which is a theory which applies to transport and zero modes. So I can refer to a work of Galetsky, which explains from a dynamical viewpoint how such type of multiscaling can emerge from equations. And the more recent theory, basically a theory which relates to something called hidden symmetry, which is basically the topic of what's next, and is basically where I leave the floor to Alexei.
switch it off. Okay, thank you very much, Simon. So in that rest of the time, I will try to, well, I first kind of try to give a conceptual summary of what Simon explained. Essentially, he explained a part of the state of art in turbulence, so how we understand turbulence, that relation between equations, observations, and theory. So what do we have? And give a motivation and plan of what we do next. So when we talk about turbulence, we already agreed that turbulence is understood as statistics of the statistical properties of the Navier-Stokes equations, incompressible three-dimensional Navier-Stokes equations in the two limits, in the certain limits. So first of all, you consider large times, so you average. Then you consider small viscosity or large Reynolds numbers, and this is very or large Reynolds numbers, which is mathematically the same, but this is what actually happens physically, and this is what we like to, how to like to formulate mathematically. And here we're really at in the place of application because Reynolds is huge in application. So it's already, as Simon told, that when you go by bicycle, you get Reynolds like 10⁻⁷ maybe, yeah? And then in weather prediction, you get Reynolds 10⁻⁻10, 10⁻12. So actually what we will see is that small number is not actually, or large number is actually not a Reynolds, but log of the Reynolds. So usually when we see it very large Reynolds numbers, we say that not just Reynolds is large, log of Reynolds is large. Okay, and then in principle, there is one more limit that always implied is that we consider small scales. So small scales. Okay, so this is average. So this is a problem we want to study. So this is kind of our goal. The large piece of the and then we have observations. So observations tells us a lot of things. So observations come from essentially two different sources. One source is a real experiment, because it turns out that Navier-Stokes is really, well, at least it's not, it's actually, we expect, so it's not exactly proved, but because of many years, but we expect that Navier-Stokes is really what explains the motion of air and water, which means that we have a lot of experimental evidence. We just measure. And the next type of measurements are numerical measurements. And like in last decade, with the supercomputers, new method, you really can have very good numerical results. Just last decade, actually. So we have enough numerical results to probe this behavior. So experiment and numerics. And there are different things that we want to. So what properties do we have? So first of all, we certainly know that everything is probabilistic. So the description is probabilistic. So that's a question. So so every line that I will put here is observation which we have to get from a left side. So first is probability. But having probability is something natural, right? Because if you take average of long time in a chaotic system, you come to probability. So measures usually come naturally. The next thing is intermittency. And intermittency is exactly what Simon was talking about, which is another name is scaling anomaly. Scaling anomaly. So this zeta piece. So scaling. So it turned out that structure functions they there's no example here. So the structure functions they behave with changing L as a power law with certain exponents. Why we're interested in at all in structure functions, physicists like it very much because this is what is can be measured. Well, which was measured and can be measured with a good accuracy, and you indeed compute exponents. They have a lot of universal properties. They don't depend on forcing conditions and so on. So this is what we measure. So this is kind of our testing of any theory, whether the theory gives the right at all give scaling exponents or not. And there are other questions which actually we did not touch. For example, dissipation anomaly. Probably we'll talk about this. But there are several other issues. But we will be mainly focused on intermittency. So this is another part. Okay, so what Simon was explaining in the free lectures are the models. So the probabilistic models. So probabilistic models, so there was this Gaussian heat, which gives already some properties of this observation, and then today was multifractal or multiscale, multifractal model. So the product of random variables with random exponent especially. So you can get it in different way. And in this probabilistic model, so what they say is that, okay, these probabilistic models gives what we want. So if you cook up the model in very different ways, so essentially this is the whole field of activity with large practical importance. It's hard to simulate Navier-Stokes. So let's just essentially hard to Navier-Stokes because you need to have many scales, and scales are important. So let's just make a probabilistic model that just give us something looking like the right the right field, right in the sense of what we know. And you can do actually a lot, but actually more than we understand every time since the models are not really linked to Navier-Stokes, so you're always missing something. So more you understand, you have to improve the model. And so far, this goes very, very well, but not perfectly. Okay, but this is so what is what we want is a Navier-Stokes, right? So we want this observation to explain with a Navier-Stokes. So and there is so what is the connection between the probabilistic model and Navier-Stokes? Actually, if you look at this argument that Simon was using, essentially he never used the Navier-Stokes equation. So the Navier-Stokes was never coming. So actually only thing that he was using is the symmetries. And at the first place. And sometimes also conservation laws, like conservation of energy. So this is the third piece, and so what was done was kind of these symmetries, they motivated probabilistic model, just as motivation. They motivated probabilistic models, which already give us the observation. So symmetries are directly taken from the Navier-Stokes. So Navier-Stokes prescribes the symmetries. With the symmetries, we motivate probabilistic model. Probabilistic model will give us what we want. But what we want is, of course, is if we want to have turbulence theory, we want this connection. So we want to get what we see directly from a model. So this would be a true theory. So what we, okay, no? I think this is very much linked to what Sergey was asking several times, right? So there is a noise, I think it's from, okay, so so the question we are trying to, we will now address is how to make this connection rigorous. Certainly we don't really hope just to take Navier-Stokes and derive something, because I mean that it's not excluded, but we know that now we see, rigorously we know so much things about Navier-Stokes yet, so that the question that we put here are much more complex than even what we want to understand, like existence, uniqueness, and so on. So instead of this, we put a hypothesis, which is something very, very typical that we have in many physical theories, is that we say that this property, so first what you see that these properties, these observations, we always were linking to symmetries conservation laws, not to specific equation. So what we say is that actually the properties that we want to explain are not properties just of Navier-Stokes equation and no equation else. So just we say that what we observe is not actually the exclusive property of Navier-Stokes, but a property of some class of systems, right? So which are determined by some qualitative arguments. So we say that properties of turbulence. And by properties, in this mini course, we will only address intermittency. Apply to a larger class of models. Not just Navier-Stokes. Navier-Stokes. And these models just share some properties, which share similar properties. Like symmetries, conservation laws, and so on. Etc. So here we certainly there are several problems involved. One of the problem is which properties. So which properties you need in order to take a class of models which give us what we want. And the second class is taking this class and make a connection, derive intermittency for that class. So this is what we are going to do in the next lectures, and I'm essentially will try to give a plan. I don't think there is a need to. Yeah, we'll have a plan So the plan is the following. So now we will not anymore working with really Navier-Stokes, but we come to Navier-Stokes at the moment. So we start with with a model. So what was missing here is one of the main important things which was missing is how. So Simon explained that if you have multiplicative random process or something like this, you get intermittency. But the question is how this kind of process at all comes from a Navier-Stokes equation, which is deterministic. Right? So what is the mechanism in Navier-Stokes equation which gives something like Markov process or multiplicative random process and so on. So the first thing we will just take a model, we create model by hand, which you can solve completely and see all ingredients there. So this is solvable. So this will be next lecture. This will be solvable, rigorously solvable, intermittent model. Let's say of turbulence. Turbulence in general understanding. So after this, so we will just completely solve. We will have all these properties of intermittency, and from this we will we'll get some intuition what is important, what is not. So the next lecture will be about the intermittency So the next lecture, from this solvable model, we will understand what means hidden symmetry, scaling symmetry. Still in some class of models, but already not in a single model, in a class, in what's called in shell models of turbulence. And from this, we'll see how this hidden symmetry gives us anomalous scaling. Scaling anomaly. So in this level, we will already we will identify what means properties of the models, construct the models, and then see how this. So kind of we will show how this hypothesis can be realized on some set of models. The next lecture will be the same business, hidden symmetries in Navier-Stokes. So now we will carry what we understand and put it for Navier-Stokes. And actually, it's not just carried because Navier-Stokes is more complicated than what it was. So there will be extra constructions. So we will work with Navier-Stokes. So then, after that, we will generalize. So all these three steps will be essentially technical. So we will directly derive what is a hidden scaling symmetry. So the symmetry which is not in a list of symmetries that we were given, but it's following through it under certain in certain manner. And so in each case we will have this symmetry. So after that, what we will try to understand is why it at all coming. So where it comes from, why all hidden symmetry is available in all these systems. And this will be a hidden symmetry explained by group theory. So what we will see is actually hidden symmetry which implies intermittency does not need equations at all. So that we can just directly derive these properties just from knowing group, the symmetry group. Symmetry group, commutation relations. So essentially the structure of the group have something in it which gives us hidden symmetry, essentially as a kind of quotient group. But quotient group in the situation when quotient group cannot be defined. So there is some issue. So we will want to make the quotient with respect to subgroup, which is not normal. So quotient group does not exist, as we know. But doing something extra allows us to do it. Yeah. So that's what we want to do. And then there will be other issues if we have time, other topics. So I hope that we can touch the question of dissipation range. So as we remember, Simon told that all this intermittency is at the scales L, which is much smaller than the scale at the large scale. So you take a cup of soup and roll. So this L capital is the size of the pot. But then we have intermittency at all scales up, down to something very small scales, which is called Kolmogorov scale. So this is usually 1 millimeter in real life. No? So it's usually 1 millimeter. So we want, so here we have intermittency. So we want to know what happens at smaller scales. So and how all these hidden symmetries link to this. So it's one thing, and then another thing is hidden symmetry in transport equations. And transport equations is another topic in turbulence. So where all this machinery also works. So you have intermittency, exponents, and so on and so on. But what is interesting is what we want to kind of convey is that transport equation has a different symmetry group. And different symmetry group will require different quotient, and all of the machinery will work in the same way, but you will have a different group and quotient with respect to different subgroup. And everything will be different, which kind of opens the way to other questions. So how to understand all this from a group theory and to unify probably different kind of intermittencies from on a level of group theory. So I think this is our plan, and so hopefully this is a lecture. Hope everything will be well. If we do it every point with the same as one lecture, we fit into the schedule. So we will see how we go. So see you Friday. We are back at 2:32. Friday 2:32.